Welcome back to Economics 708, How to do research in microeconomics, tips and research development example. In chapter 4, the hot topics of doing research in microeconomics. One of the hot topics that I would like to introduce to you is game theory. Game theory is very famous because of John Nash. He's the only one economist, in fact, mathematicians, that is filmed to be the movie, A Beautiful Mind. His life is very interesting. He suffered from the mental illness, but still be a genius in mathematics and created game theory. The application of game theory is enormous and very beautiful in economics and other fields of academics. We use game theory to interpret the behavior of consumers, firms, competitors, even the colleagues who coordinate in working. We use game theory to predict the actions of our component or colleagues. You can see that in reality, we don't live with just ourselves, but with other people, other side, other persons. We may compete, we may fight, or we may collaborate. We may work together. We may enjoy the happiness together. We may enjoy the profit together. Or we fight against each other to acquire the profit as much as possible. We are in many situations, but for sure, we are not alone. Game theory is a perfect theory that explains and predicts the behaviors and actions of actors or agents in the economy or in microeconomic situations. Why I encourage you to do research with game theory? Because doing research with game theory, you have the ground theory to back up your thesis. It means that it is not from the empty scratch, but from a very strong founded theory. Second, if you form a question that is very interesting to publishers, to readers, then it is easier for publication in good journal. It means a lot for the graduation of yourself. Third, how to solve the game requires data. You can use data from both the primary data from experiments and secondary data from the dataset or database. So there are a variety of methods for data collection to fulfill the research using game theory. Therefore, with a strong grounded theory, with the popularity and the interest of publishers of international journal, and with the variety of data collection method, then doing research in game theory serves your purpose to do the thesis, the research work or report, the analysis that you are supposed to present to your advisors, to the committee, or to the boss. However, doing research using game theory requires you to know about the theory. Therefore, I will show you step by step of game theory. In this lecture, I will show game theory with price competition first, and then the simultaneous game. After that, the mixed strategy and the focal point, the Pareto Optimality, the competitive game and cooperative game, and last, sequential game. All these foundations are essential for knowing about game theory. After you understand all of them, then you can think of doing a good research based on those theories. Let's proceed to game theory. First of all, I would like to introduce you to the components of the game. Game must have players, rule of the game, strategy, and payoffs. Players must have more than one player, otherwise you play with yourself and it is decision under uncertainty and it is not game theory. Rule of the game will govern the game, so who can do something and can't do another thing. The strategy is choices for action. So you can choose to do this and cannot choose that choice. So we have payoffs. Payoffs mean the results of the game that you will gain or you will lose. We have two types of the game. Simultaneous game. So repeat with me, simultaneous game. Two players or more players move at the same time. And sequential game. Sequential game. So one player moves first and other players moves later. Now we turn to the Payoffs Metric. First of all, we can see that it is the payoffs of the simultaneous game. We call it Payoffs Matrix because the layout is in a matrix form. So you can see we have player A and player B on the outer space of the matrix, and then in the inner sides of the matrix, then you can see a strategy. You can do two choices: go to university and go to airport. So then you may think of what kind of game it is. Here, it is to find each other. Player B will find player A, and player A will find player B at the same time without communication. They lose the cell phone and they cannot appoint where to meet. So they have to choose where to go. If one player go to university and another player go to university too, then they both happy. A happy and B happy, that's payoff. You can see that if A go to university but B go to airport, A not happy and B not happy too. That's also the payoff. So you have the positive payoff, A happy, B happy, and the negative payoff, A not happy and B not happy. Then you can see all the payoffs in the matrix. If player A go to the airport and player B go to university, they both unhappy. But if they choose the right place together, player A go to the airport and player B go to the airport, then A happy and B happy. These are the payoffs metrics for simultaneous game. Now we turn to the payoffs tree for sequential game. We don't call it payoffs matrix anymore, but payoffs tree because it looks like a tree. Now player A moves first and player B moves later. Player A decides to go to university. Player B, and now it is easy. He or she can follow to go to university too. And payoffs A happy and B happy. Player A moves first. Then if A go to airport, now what is the decision of player B? Player B go to airport too. So they both happy. But what if player A makes wrong decision? For example, player A goes to university, but player B goes to airport. Now, with something miscommunication, then they are both unhappy. And the last one, if player A goes to airport, but player B goes to university, they are both unhappy as well. I would like to apply the game theory on price competition. In last lecture, we discussed a lot about the airlines industry, and I put some questions into that lecture. So, would airlines compete with price competition? If so, can we apply the game theory on price competition? We can see that the number of players, now we have two players, A and B. You can imagine of airline A and airline B. Anything, but now we just limit ourselves to just two players. Here are the rules of the game. It is said to be the sequential game and allow A to move first. Then, winner takes all. It means that we have just only one winner and the winner takes everything, leaving the loser takes nothing. But if no single winner, means they are draw or tied, both take half. The strategy means the choices that can do or cannot do. Now they can reduce the price or keep the price stable. And what are the payoffs? The payoffs are the market size of 100 million baht. That's the winner will take all, but loser takes nothing. So we can think of the sequential game. Now we look at the payoffs tree. It is the price competition and player A moves first. It means that player A can choose to reduce the price or keep the price. But player B, if A reduces the price, B has to reduce the price too. Otherwise, B will suffer and takes nothing. You can see at the payoffs, reduce the price by A and then reduce the price by B. A takes half and B takes half. Why? Because if no single winner, both takes half. Correct. Then if player A reduce the price but B keep the price, then A takes all because A is the winner and B is the loser and B takes nothing. Now we think of A if A keeps the price but B reduce the price. What would happen? A will turn to be the loser and takes nothing. But now B will turn to be the winner and takes all. And A, if A keeps the price and B also keeps the price, they share both winner and they share half of the market. If the airlines has to make decision on this price competition, what do you think is the result of the game? You can see that we have the price competition model called the Bertrand price competition model. Here, Bertrand suggested that they will reduce the price until the price equal to the AC. And by the assumption that the cost structure of both players are the same. You see on the screen that MC and AC of player A look similar to MC and AC of player B. That's the cost structure, the same. And here, if price of A is above the bottom of AC, what would happen? A will get excess profit and B can still lower the price. If B can still lower the price, A will lose everything because B will be the winner. You understand that? Now, if the price of A is at the bottom of AC and the price of B is also at the bottom of AC, there is no more room to reduce the price because here it is the normal profit. If you reduce the price lower than this, you will lose. You will have the loss. So it is unreasonable to reduce the price lower than this point. It is the last point to lower the price. Therefore, it is the last price. The last price is at the AC, at the bottom of the AC, and player A gets half of the market and B gets half of the market, but regardless to any size of the market, 100 million baht or 1000 million baht, they both get just the normal profit because the price equals to AC. No excess profit, just the revenue that they can get from the market, half of the size of the market of the revenue, but the profit is just only the normal profit. You see the point. In price competition model, both players suffer. They gain just only the revenue, but the normal profit in the end. So, under price competition, people don't like the situation, right? We have Michael Porter's. Michael Porter suggested the low-cost strategy. Michael Porter is a very famous professor in the world. He gives a talk, cost 1 million baht per talk. Thailand invited Michael Porter to come to give a talk once, and we pay 1 million baht for his talk. That's Michael Porter. Michael Porter is a hero of me. He didn't get the Nobel Prize, but he suggested a very clever model to do business. We call the 5 force model. And if I have time and opportunity, I will introduce the 5 force model to you someday. But today, the first thing that I would like to introduce his strategy is the low-cost strategy. It is based on the Bertrand price competition model that we have learned later. And you can see that Michael Porter suggests that if you can lower the cost, lower than your competitor's cost, what would happen? You see on the screen. Here, AC of player A is lowered to be AC low cost. Now, A has more room to reduce the price. while player B do not have any room to reduce more price lower than his or her AC. Now, the price of A can be lowered than price of B because of the lower cost, the lower AC. And A can take all of the market because A has the price under the price of B. A is the winner in this price competition. But you may think that A takes all the revenue in the market, leaving B just to be the loser. So what would happen next? Because now player A just get the normal profit. You see something. If player A just lower the price a little bit than the price of B, but it's still higher than the AC, now player A can get the excess profit. You see the point? There's a room for having the excess profit. Second, if now it is the situation of two players, they are in duopoly in price competition. When B is the loser and gains nothing, B gets heavily lost, and B has to go out of the business and allowing A just to be the one seller in the market. What would it called? It is the monopoly. A now is the monopoly of the market, and you can see that the monopoly always gets the excess profit. A can eliminate B out of the business by lowering the cost and reducing the price. A is the winner, B is the loser. So Michael Porter suggested that as long as you can lower your cost, you will have more opportunity to be the winner in the game. This is very important. If you can think of the airline and you can see the low-cost airline coming to compete with price to the full-service airline, what would happen now? What airlines survive in the market now? Can you name some? Yes, you can find that those are low-cost airlines. Is it like the Michael Porter's low-cost strategy? It is. This is microeconomic theory. This is the power of microeconomics. And this is the power of game theory. That's Michael Porter's power to suggest that what should be done in business. In the simultaneous game, we call the components of the game. First, we have players. In this game, we have more than one player as usual. 2. Rule. The rule of the game. All players move at the same time. This is very specific to the simultaneous game. 3. Strategy or choices for action. In this simultaneous game, players have strategy or choices for their actions. And 4. Payoffs for all players. In the end, all players will realize their payoffs. Looking at the Payoffs Matrix for the simultaneous game, you see we have player A on the left-hand side and player B on the top of the table. And then we have two strategies. First, go to university, and second, go to the airport. You are familiar with these payoffs because this is an example in last lecture. So you see the payoffs in the matrix. If both player A and player B go to university, they are both happy. A happy and B happy. But if they miss to meet each other, then you see that A will not happy and B will not happy too. Now, we turn the happiness into some numbers. You see that happiness is for 100. The unit of happiness is utils. Economists generate the units of happiness or the utilities. Then the unit of the utility is utils. Therefore, if A go to university and B go to university too, A and B will gain 100 utils. But if player A misses to meet player B at the airport or university, then player A is unhappy and player A lose 100 utils or minus 100. Then player B also loses 100 utils as well. Therefore, the payoffs of A and B is minus 100 and minus 100 in that case. Here you see that we have 4 cases of the results. Now, we turn to how to solve simultaneous game. We solve the simultaneous game by reaction function. I will introduce you to the reaction function. Here, first, we find the reaction function of player A. So, we recall the Payoffs Matrix of player A and player B for the game of meeting each other at the university or the airport. Here, the reaction function begins with if player B do something. For example, in this case, if player B go to university, what would player A do? So you see that the first item or the first number in the bracket is the payoff of player A. Then you compare 100 and minus 100. If player A go to university too, they are both happy and player A will get 100 utils. But if player A go to the airport, they miss to meet each other and then player A will get minus 100 utils. So what is better between 100 and minus 100? You see that 100 is better. Therefore, if player B go to university, then player A will go to university too. This is the reaction function of player A. Now, we turn to if player B go to the airport, and then you see that player A have to compare with the payoffs of minus 100 if he or she goes to university and positive of 100. So you see that this is the better choice because 100 is much more than minus 100. Therefore, player A will choose to go to the airport. Therefore, the reaction function in this case, if player B go to the airport, then player A goes to the airport too. Here we write the reaction function of player A like this. We have 2 reaction functions. Reaction 1, if B goes to the university and then A will go to university too. And the reaction function number 2, if B goes to the airport, then A will go to the airport too. Here we find the reaction function of player B. We use the same method, if and then. First, if player A goes to university, then B compare with 100 and minus 100. You see that B will gain 100 if B goes to university too, but will lose 100 utils if he or she goes to the airport. Therefore, which is better? Yes, going to the university is better because 100 is more than minus 100. Therefore, If player A goes to university, then player B will go to university too. This is the reaction function of player B. Here we are. If player A goes to the airport, then B has to compare between minus 100 and plus 100. Therefore, player B will go to the airport too, because 100 is more than minus 100. That's correct. Therefore, the relation functions of player B. We have two cases of the relation functions. First, if A goes to university, then B goes to university too. And if A goes to airport, then B goes to the airport. These are relation functions of player B. Now, you know about the relation function, so let's apply it in these following games. Game number 1. Game with one equilibrium. Suppose we are playing the investment game between player A and player B. So you see the strategy here. Both players can build big factory or small factory. Therefore, the choices of player A is big factory and small factory. Player A has to choose between big factory or small factory. And in the same situation, player B will have to choose a big factory or small factory too. They choose at the same time, so it is the simultaneous game. Simultaneous game is player A and player B move at the same time. Now, we look at the payoff in the matrix. You see that if player A built a big factory and player B built a big factory too, they will have just only 100 and 100 million baht for the profit. Why? Because the supplying is very much. Here, if the greater supplying is supplied into the market, then the price drops and the profit of player A and player B will be lowered. So, what if player A and player B build small factories? You see that both A and B will gain 250 million baht. So the situation is better. Here you see 4 small factories, then the numbers of supplying which will be sold into the market will be small. Therefore, the price will be high. And the profit of player A and player B will be high as well. Therefore, if we look at this game, player A and player B, must choose small factories. But what would happen in the game, we will see next. But let us look at another choice. So small factory and big factory. So what would happen? You see that the supplying is not so many or not so little. Therefore, the price is not so high and the price is not so low. So the price is in the middle. And both of them will gain something. But the big factory will gain more because of the numbers of supply, which is greater. So the price is good, and player with big factory have many more products to sell. Therefore, they gain more. So in this case, you see that if player A has a big factory and player B has a small factory, then A will gain 350, while player B will gain just only 50. But in another case, if player A has a small factory and player B has a big factory, then player A will get just only 50 and player B will get 350 in the unit of million baht. These are something that will change the game. So, to solve the game, especially the simultaneous game, you have to find the relation functions. Now we find the relation functions of player A. So we begin at if player B do something, then what would player A do? So if B builds a big factory, then A has to compare between 150. So you see that the payoffs on the left hand side and in the bracket is belongs to player A. So here 150, which one is better? You're right, 100 is better. Therefore, if player B builds a big factory, then player A has to build a big factory too. Another relation function. If player B builds a small factory, then player A has to compare between 350 and 250. Which one is better? So it is obvious that 350 is better than 250. Therefore, player A builds big factory. You see that the relation function of player A. Now, the first relation function. If B builds a big factory, then A builds a big factory too. And the second relation function. If B builds a small factory, then A will still build a big factory. We call it the dominant strategy of player A. No matter what B chooses, A will choose the same strategy. In this case, big factory is the dominant strategy of A. You recall that no matter if B builds a big factory or a small factory, then A will still build a big factory. So no matter what B chooses, whether it is the big or small factory, A will choose the same strategy, which is the big factory, always. So the big factory is the dominant strategy of A. Now we turn to the payoff matrix again. So we find the relation functions of player B. We begin with if player A do something, then player B reacts to do something. Here, if player A builds a big factory, then player B will compare between 150. The payoff on the right hand side in the bracket is belonged to player B. Therefore, player B has to compare between 150. Which one is better? 100 is better, of course. Therefore, if player A chooses to build a big factory, then player B will choose to build a big factory too. Another relation function. If player A builds a small factory, you have to compare between 350 and 250 for player B. Which one is better? You see that 350 is better. You are right. Then if player A builds a small factory, then player B builds a big factory. Here is very crucial for the answers of the game. You see that player B has the dominant strategy too. It is, no matter what A chooses, B will choose the same strategy. In this case, B has to choose big factory, and big factory is the dominant strategy of B. No matter A chooses big or small factories, B will choose always the big factory. So big factory is the dominant strategy of B. Very good. Now we find the equilibrium of the game. It is obvious when A always chooses big factory and B always chooses big factory too. So both players end up to build big factory. Therefore, big factory and big factory will be the equilibrium of the game. So it is the answer of the game. The equilibrium of the game means the answer of the game. So the game ends up at A builds big factory and B builds big factory. And the payoffs, or the gains that both player A and player B will get in this game. They both gain the payoffs 100 and 100 million baht. So player A gains 100 and player B gains 100. You may think of a better payoffs 250 and 250 if both build the small factorings, but it is not the equilibrium of the game now. Why? Because A has the dominant strategy to build a big factoring, and B has also the dominant strategy to build a big factory. So we will discuss later how to gain the highest payoffs. But now you can see that the equilibrium of the game doesn't allow both players to have the highest payoff, which is 250 and 250, but they gain just only 100 and 100. Very surprising, very strange, but it is real. Now, I will introduce you to the Nash equilibrium. The game has Nash equilibrium when the equilibrium comes from the matching between reaction functions of all players. The matching of reaction functions, what it is. So you see the reaction functions again here. The reaction function of A states that if B builds a big factory, then A builds a big factory. And reaction of B says that if A builds a big factory, then B builds a big factory. So you see the relationship between those reaction functions here. If you think about A, if A builds a big factory, then B builds a big factory, and if B builds a big factory, then A builds a big factory. Therefore, for the reaction function of A, if B builds a big factory, then A builds a big factory, and if A builds a big factory in reaction function of B, then B will build a big factory. So you see the linkages between the reaction function of A and reaction function of B. And now you see another linkage. Here, if A builds a big factory, then B builds a big factory. And you can repeat, if B builds a big factory, then A builds a big factory. You can repeat this again and again and again and again. Therefore, you can read it through and smooth. If B builds a big factory, then A builds a big factory. And if A builds a big factory, then B builds a big factory. So it can be repeated. In this payoff matrix, you see that if player B chooses to build a big factory, then player A will choose to build big factory. And if player A chooses to build a big factory, and then player B will choose to build big factory. So if B big factory, then A big factory. If A big factory, then B big factory. So you can find this matching of reaction functions. You can say it smoothly. So it is the circular flow of the reaction functions here. If B big factory, then A big factory. If A big factory, then B big factory. And you can repeat this forever. So the point that you can repeat these reaction functions forever and smoothly with the circular flow of these reaction functions, then that is the Nash equilibrium. You may notice that if A and B has dominant strategy, it means that both player A and player B have the dominant strategy, which is big factory. Then the Nash equilibrium will be just only one point in this payoff matrix, which is big factory and big factory. Other points will not be the Nash equilibrium. This is why the choice of small factory and small factory, which may yield higher payoffs, will not be chosen, because it is not the equilibrium of the game. It is better in terms of payoffs, but it is not chosen by player A and player B. Therefore, it is not possible for this choice to happen. Something that is better, but impossible to happen. It's not a thing that we can have in our life. Therefore, it may be a dream, or it may be ideal to have that point, but in reality, we cannot have that point. The reality is that we have a big factory and big factory, because this is the highest rational choice. So it is possible to happen, because it is not just because of you. It's because of another player, your opponents, or your teammates, or your friends. It depends on others. So game theory teaches you that it is not just because of you in the determination of the payoffs or the results of the game. It depends on another side, which will determine the results of the game. Here you see that if you try to build a big factory and you expect that you may gain 350 if another player just builds a small factory. This is just the expectation, but it is not true in reality, because other players have to think too. And the most rational choice for him or for her is also the big factory. And you end up with just only 100 for your payoffs, because another player chooses to build a big factory too. This is game theory. The game that yields the payoffs depending on the action of another players. You see that it is not just because of you, but because of all the players in the game that determine the result of the game. We use the mixed strategy when there are more than one Nash equilibrium or there is no Nash equilibrium. We solve the game by assigning probability, and we find the expected payoffs. Then the equilibrium is at the highest expected payoffs of all players. Now recall the game number 2, the meeting point, when we have player A and player B, and the strategy is going to university and to the airport. The payoffs are on the screen. If they meet each other, then they will gain 100 U-tunes for both players. But if they don't meet each other, then they will lose 100 U-tunes for both players. Here we have the reaction function of player A. If player B goes to university, player A will go to university, and then he or she will gain 100 U-tunes. But if player B goes to the airport, then player A goes to the airport too, and he or she will gain 100 U-tunes. So we have two reaction functions of player A. Then we turn to see the reaction function of player B. If player A goes to university, then player B will go to university too, and he or she will gain 100 U-tunes. But if player A goes to the airport, then player B will go to the airport too, and he or she will gain 100 U-tunes. So there are two reaction functions of player B. We compare the reaction functions of both players. So you see that we have reaction function number 1 of player A and reaction function number 1 of player B in the same cell, which is going to university and going to university. This is the first pair of reaction function. And the second pair of the reaction function is at going to the airport and going to the airport. you see that the duration function of player A is the blue lines, and duration function of player B is the brown lines. So the brown and the blue are in the same cell. Number 2 and number 2 are in the same cell. So this is the second pair of duration functions of both players. You see that we can match duration functions of player A and player B in the same cell. So number 1 and number 2. So you see that going to the university and going to university, we have number 1 and number 1 stay close to each other, stay together in that cell. So this is the Nash equilibrium. And you see that number 2 is with number 2 in the cell indicating going to the airport and going to the airport. So this is the second Nash equilibrium. So you see this is the situation which have two Nash equilibriums. You see that the Nash equilibrium is the matching between the duration functions. So if you can find the duration function number 1 and duration function number 1 of both players in the same cell, that is the Nash equilibrium. And you see that we have the duration function number 2 and duration function number 2 of both players in the same cell as well, but elsewhere. That is another Nash equilibrium. So here we have two Nash equilibriums. The first equilibrium, you can see the flow or the continuous duration functions, the matching between them. We can read if A goes to university, then B goes to university, and then if B goes to university, then A goes to university, and you can repeat this forever. So yeah, it is the flow of the duration functions. So you can match these duration functions, and this is the Nash equilibrium number 1. We have the second Nash equilibrium here. If A goes to the airport, then B goes to airport. If B goes to airport, then A goes to the airport, and you can repeat it. If A goes to airport, then B goes to airport. If B goes to airport, then A goes to airport, and you can repeat it forever. So you can see the flow of the duration functions, the matching between them. Therefore, this is the second Nash equilibrium. Therefore, there are two possible places that player A and player B may meet each other, but we still don't know exactly where they will meet, the university or the airport. Thomas Chirling, he got the Nobel Prize in Economic Science in 2005 for having enhanced our understanding of conflict and cooperation through game theory analysis. He suggested the focal point, and he called it the focal point equilibrium. Unfortunately, he has passed away in 2016. He said that one of the many Nash equilibria might stand out from the others due to some asymmetry that is common knowledge to the players. If the players think the same or know each other that the other side tends to go to university first and then go to the airport later, or he or she may have some activities to do at the university. Therefore, the choice of going to university stands out with higher probability. So, if we assign the probability, you can see that going to university will have the higher probability, for example, 0.8, comparing to the probability to go to the airport, which is 0.2. you see that the summation of probabilities must be 1. The probability of going to university 0.8, the probability to going to the airport 0.2. 0.8 plus 0.2 equals to 1. And we have the probability of player A going to university 0.9, and then the probability of going to the airport of player A 0.1. 0.1 and 0.9, the summation is 1. Therefore, you can see that the choice of going to university stands out from going to the airport. Here is the focal point, as suggested by Thomas Chirling. Recall the payoffs. Here you see that if they meet, they will have both 100 utils. But if they don't meet each other, then they will lose 100 utils. Now we calculate the expected payoffs, or the payoffs adjusted by the probability. In economics, when you use the word expected, it means that we have the probability to get involved in that calculation. You must remember this. Expected return is the return adjusted by probability. Expected payoffs is the payoffs adjusted by probability. Here we have the probability, and we can calculate the expected payoffs of A. If A goes to university, and expected payoff of B if B goes to university. So in this first cell, you see that if player A goes to the university, what would happen? We have the probability of 0.8 that B is going to university too. Therefore, if B goes to university, A will get 100 utils. 100 utils with the probability of 0.8. Therefore, the expected payoffs is 80. So you'll be multiplying the total utilities 100 with the probability 0.8. 100 times 0.8 equals to 80. Look, the payoffs of player A, you must use the probability of player B to calculate, because it is not depending on A but B to make that payoffs happen. A will go to university, okay, fine, but B will go to university with just the probability of 0.8. Therefore, the payoffs of player A depends on the probability of player B. Another example, the expected payoffs of player B depends on the probability of player A. So you look at the left hand side and you see the probability of player A to go to university is 0.9. And if player B go to university and player A goes to university, player B will get 100 utils. But expected payoffs, or the payoffs adjusted by the probability, will be 100 utils. This is the full utilities that we can get times the probability of player A going to university, which is 0.9. Therefore, 100 times 0.9 is 90. So this is the expected payoff of player B if B goes to university. Here, in the second cell, you see that if player A goes to the airport, but player B goes to the university, you see that we have minus 100 utils as the payoff, and it is the probability of 0.8. So it is 80% that B will go to the university if A goes to the airport, and it is 80% that B will go to university. It means that A tends to lose 100 utils but with the probability of just 0.8. So A can expect that he or she may lose 80 U-turns. On the screen it is minus 80. So this is the expected payoff of A if A goes to the airport but B goes to the university. Here you see the expected payoff of B. If B goes to university and A goes to the airport, B will lose 100 U-turns for the full payoffs. But just only the probability of 0.1 or just 10% that A will go to the airport. Therefore, B can expect that he or she will lose just only 10 U-turns or minus 10. For the calculation of minus 100 U-turns times the probability of 0.1. So you see again that expected payoffs of one player depends on the probability of another player. Here we turn to the third cell. The expected payoff of A if A goes to the airport, and then if A goes to the airport, he or she will gain 100 U-turns. If B goes to the airport too, but B will go to the airport with the probability of just 0.2 or just 20%. Therefore, A can expect the return or the payoffs just only 100 times 20%. It is 20. You see that here the expected payoff of B. If B goes to the airport too and A goes to the airport, B will gain 100 U-turns, but with a probability of just how much? 0.1. 10%. Therefore, B can expect to gain just only 10, which is 100 times 0.1. You see that the name expected payoffs means that A can expect the gain or the lose by the full payoffs times the probability. And B can also expect the payoffs by multiplying the full payoffs with the probability. Here it is the meaning of expected payoffs because both players can expect their payoffs. Now we turn to the last cell. We see that if A goes to university but B goes to the airport, of course A will lose 100 U-turns, but with the probability of just 0.2. Therefore, A will lose. A can expect to lose 20 U-turns. And if B goes to the airport but A goes to the university, B will lose 2 minus 100 U-turns, but with the probability of 90%. So B can expect that he or she will lose 90 U-turns. We come to write the expected payoffs into the matrix instead of the full payoffs. You see that now it is not 100 and minus 100, but the expected payoffs that we have calculated in the previous screen. You see that we have to compare. Now look at player A. Player A compares the payoffs. We have 4 payoffs for player A. Here, going to university and going to university, player A will get 80 U-turns. If player A goes to university and B goes to the airport, then minus 20. If player A goes to the airport and player B goes to university, minus 80. And player A goes to the airport and B goes to the airport, plus 20. Which one is the highest? the highest expected payoffs of A. So you see 80 minus 80 minus 20 and 20. So 80 is the highest. We maximize the expected payoffs. Therefore, player A will go to university because he or she can expect the highest payoffs. Now we turn to player B. Player B compares his or her payoffs, which is 90 minus 90 minus 10 and 10. Which one is the highest? Of course, 90 is the highest. Therefore, player B will decide to go to university because of he or she can expect the highest payoffs. So you see, when player A decides to go to university and player B also decides to go to university, they meet each other in the end, and we recall the original payoffs of 100 and 100. A will get 100 and B will get 100 U-tunes. And the equilibrium, the answer of this game is in the bracket. You see university and university. It means that A will choose to go to university and B will choose to go to the university. They meet each other and the payoffs equals to in the bracket. So you see 100 and 100. A will get 100 and B will get 100. This is the solution of the game. And we call it the focal point equilibrium, as Thomas Chirling initiated and suggested us to use the focal point equilibrium to solve the game with more than one Nash equilibrium. Now, we look at the game number 3, Catch Me If You Can. It is the game between police and the thief. You see that they don't want to meet each other, especially the thief don't want to meet the police. But the police want to meet the thief. You see that we have two strategies, going to town and going to forest. If police goes to town and the thief goes to town, they meet and police will get 500 U-tunes because they can arrest the thief. But the thief will lose minus 500 U-tunes because he or she will be arrested. So we have one side that get positive payoffs and another side get negative payoffs. You see, if they don't meet, for example, police goes to town and the thief goes to the forest, then the police cannot arrest the thieves. The thieves has positive payoffs of 500 U-tunes, but the police must be punished because he or she cannot catch the thief. Then the police will be punished with sadness by 500 U-tunes or minus 500. You see, in other payoffs, if police goes to the forest and the thief goes to town, then you see that it is minus 500 for the police and 500 for the thieves because the thief will go away and will not be arrested. Good for the thief. But if the police goes to the forest and the thief goes to the forest too, then this is good for the police and the police will catch the thief and the police will get 500 U-tunes while the thief will lose 500 U-tunes. This is game number 3. Catch me if you can. You can notice that this is the zero-sum game. when one side get positive outcome and another side get negative outcome. So the summation of the payoffs would be 0. If one side gets the positive payoffs, then another side will lose and get the negative payoffs. This is called the zero-sum game. So you see in all the cells of the payoffs, the summation of payoffs of A and payoffs of B, or payoffs of police and payoffs of the thief will be 0. Here you can see that in stock market, when someone gets the profit and another one must have the loss. So money in one pocket goes to money in another pocket. This is zero-sum game. We recall the payoffs again, 500 and minus 500. Now you remember the payoffs. Now you see the duration function of the police first. So the police think if the thief goes to town, then he must compare 500 if he goes to town and minus 500 if he goes to the forest. And you see that it is better going to town because 500 is more than minus 500. And if the thief goes to the forest, the police think again. If he goes to town, he will lose 500. But if he goes to the forest, he will get 500. Therefore, the duration function of the police is if the thief goes to the forest, then the police goes to the forest too. Now, the duration function of the thief. If police goes to town, the thief don't want to meet the police, then the thief will go to the forest. And if the police goes to the forest, then the thief will go to town to escape. Here we see the comparison of the duration functions. You see that now we have no place that duration function number 1 stays together, and we have no place that duration function number 2 stays together. You see that duration function number 1 stays in 2 cells and duration function number 2 stays in 2 cells. So there are no matching between the duration functions, so there is no Nash equilibrium. In this situation, comparing to game number 2, you see that number 1 stays together in 1 cell and number 2 stays together in 1 cell. But this is not the case of game number 3. You see that they are separate to each other. And there is no pair of the duration function in the same cell. So there is no Nash equilibrium in this game. You can see that if police goes to town, then thief goes to the forest. And if police goes to the forest, then thief goes to town. So you cannot find each other here. And if police goes to the forest, then thieves go to town. And police goes to town, then thieves go to the forest. And then you may think of, then thief goes to the forest, and then the police goes to the forest, and then thief goes to town. So you cannot match the duration functions. It is not smooth and flow smoothly like in game number 2 that you can repeat it forever. But here you cannot find the flow, you cannot find the repeat. So it is not the Nash equilibrium because you cannot match the duration functions. Therefore, there are no place that they will meet each other, and there is no answer whether they meet each other or not. Here we assign the probability. When there is no Nash equilibrium, we assign the probability. And we think that the thief will go to town with the probability of 0.1. And he or she will go to the forest with the probability of 0.9. Now, we assign the property of police too. Here, the probability of going to town of the police is 0.4, and the probability of going to forest is 0.6. Why? This is just the assumption, but we have some reasons behind that. The thieves may think that going to town is more risky because other people may recognize him or her. Therefore, he or she will choose to go to the forest where no one is there. And the police think, it is easier to go to town, but it may be better to go to the forest. So in fact, he or she think of 50-50, but place the more weight to go to the forest, but still think of going to town. So in his mind, he's like 50-50. He cannot choose whether to go to the town or go to the forest, but he think of the forest more than the town. Then the probability of 0.6 is for the forest and 0.4 is for the town. Now we calculate the expected payoffs of the police and the thieves, and here we see that the expected payoff of the police if the thief goes to town, depending on the property of the thief, so it is 500 if he can catch the thief times 0.1, which is the probability of the thief going to town, then it is 50. And for the thief, he will lose 500, but the probability of just 0.4. Using the probability of the police, you see that now we have just only minus 200. And here, the second cell, we calculate the expected payoffs again, and we see that the expected payoff of the police if the thief goes to town is that minus 50. But expected payoff of the thief if police goes to the forest is 300. Can you explain why we calculate expected payoff like this? You see that the police expected that if the police goes to the forest and the thief goes to town, he will lose 500, but with the probability of just 10%. Then the expected payoff is just minus 50. And the thief expected that if he goes to the town and the police goes to the forest, he will gain 500 with the probability of 60%. So he will gain 300. Now, if the police goes to the forest and the thief goes to the forest too, then the police will gain 500 because he can catch the thief with the probability of 90%. Then the police will gain 450 U-tunes. But for the thief, he expects that if he goes to the forest and the police goes to the forest too, he will lose 500 with a probability of 60%. Then he knows or he expects that he will lose 300 U-tunes. And for the last cell, the expected payoff of the police if he goes to the town and the thief goes to the forest, he will lose 500 with a probability of 90%, which is the expected payoff minus 450 U-tunes. And the expected payoff of the thief when the police goes to town he will escape and he gains 500 with a probability of 0.4, 40%. Therefore, he expects that he will gain 200 U-turns. Now, I ask you, who assigned the probabilities? You or teachers or who? So you see that this is the probability in the mind of the players. The police expect that the thief will go to town with probability of 0.1 and he expects that the thief will go to forest with the probability of 0.9. He reads the thief's mind. He expects the probabilities of the thief. The thief may think like that and the police reads the mind of the thief. Here is the secret of game theory. Reading the mind of other player. The thief reads the mind of the police. He knows that the police is somehow 50-50 to choose the town or to choose the forest. But he knows that the police may place the higher weight for the forest. Therefore, he expects that the police going to the forest with the probability of 60% and going to town with 40%. So this is reading the mind of the police by the thief. It is the thought of the police, but the thief reads that thought, read that mind. It is like the game theory that we call I know you, you know me, and I know that you know me, and you know that I know you. This is the game theory. Very interesting. The players know each other, and they know that the other side knows each other too. Here, we write the expected payoffs or the adjusted payoffs by the probability instead of the original payoffs. And you see that the police will choose between 50 minus 50 minus 450 and 450. So what is the highest expected payoffs? Of course, it is 450. So the police will go to the forest. This is the decision of the police to choose the highest expected payoffs because he or she can expect the highest outcome of his action. If he goes to town, he expects that the highest outcome is just 50. But if he goes to the forest, then he expects that the outcome is 450. And the thief, he compares between minus 200, 200, 300 and minus 300. And he makes the decision to go to town because of the highest expected payoffs. You see that if he goes to town, he expects that the highest payoff he will get is 300. But if he goes to the forest, the highest expected payoff is just 200. Therefore, going to town is the better choice. He or she will make decision to go to town. So the equilibrium is police goes to the forest and thieves goes to town. And we see that the original payoff states that the police will lose 500 and the thief will gain 500 U-turns. So the thief escapes. And the police cannot catch the thief. So you see on the bottom of the screen, the equilibrium is at police going to the forest and the thief goes to town. And the payoffs record the original payoffs. You must answer with the original payoffs, not the expected payoffs. This is very careful. You must be very careful about this. So the payoffs, then the police will get minus 500 or lose 500 U-turns, and the thief will gain 500 U-turns instead. So You may remember that this is a zero-sum game. Now, we are at the end of the class, and what we have learned in this class. First, we have the mixed strategy, and the mixed strategy occurs when there are more than one Nash equilibrium or there is no Nash equilibrium at all. Second, the mixed strategy can be solved by the focal point equilibrium suggested by Thomas Chirling. And third, the focal point equilibrium can be found by maximizing the expected payoffs of each player, which is the payoffs adjusted by probabilities. So you have assigned the probabilities and calculate the expected payoffs of each player, and then you find the highest expected payoffs of each player, and that is the focal point equilibrium and the solution of the game. I have the challenge for you. In game number 3, catch me if you can. Can you find the probabilities of the police and the thief that make the game end up without the focal point equilibrium? So you answer the probability of the police going to town is how much, and then the probability of the police going to the forest is how much, and also the probability of the thief going to town and the probability of thief going to the forest. And with these probabilities, you cannot find the focal point equilibrium. This is the challenge. Recall the original payoffs here, and you add the number of probability, and you make the game cannot be solved. The Pareto Optimality can be seen as the best solution that the game can yield, or it can be called the win-win situation, or it is the maximized social benefit. Technically, it is defined as a player cannot gain more benefits unless making another player lose some benefits. The competitive game. In the game, each player competes for the best solution for just his or her benefits. No player communicates to each other, and no one cares to calculate the social benefits. However, in cooperative game, each player cooperates with other players for the best solution for all the players. All players communicate to each other, and everyone cares to calculate the social benefits. I will introduce you to game number 4, Prisoner's Dilemma. In this game, we have Agent A and Agent B as players, and we have strategies for them to confess or not confess. Both agents are secret agents and working for our country. They are working in another country and search for secret information. They are arrested and separated to different rooms. The officers of that country ask whether they are secret agents or not. They have two choices: confesses or doesn't confess. However, the payoffs of the answers are very different. If both of them confess, then the other country will know that they are secret agents And the punishment for the secret agents are heavy. They must be punished by minus 500 U-tunes. Yeah, very heavy punishment. Both of them will lose 500 U-tunes if both of them confess. However, if both of them don't confess, they must still be punished because they access to some secret places and to something strange and try to search for some secret information which is prohibited by law. Therefore, the punishment is still there, but not so heavy. Both of them will be punished by minus 200 U-tunes. Here are the payoffs of the choice of not confess. There are options for them. It is very clever for the officers of that country to offer this option. The option is, if one agent confesses, but another agent doesn't confess, the one who confesses will receive a half punishment, which is just minus 100 U-tunes. But the one who doesn't confess will be punished more, which is minus 800 U-tunes. Why? Because one agent confesses that both of them, not just only that agent, but both of them are secret services. Then the other country now knows that both of them are secret services, and the one who doesn't confess must be punished more. What would happen to this game? Can you guess the result? To solve the game, we take a look at the relation function of agent A first. What if agent B confesses? Agent A has to compare between to confess or not confess, which is minus 500 and minus 800. It is a better choice to choose minus 500 over minus 800. Therefore, agent A chooses to confess. This is the first relation function. The second relation function of agent A. What if agent B doesn't confess? Agent A has to compare between minus 100 and minus 200. And here it is clear that minus 100 is the better choice, and agent A chooses to confess. You see that to confess is the dominant strategy of agent A, because no matter what agent B chooses, agent A will always choose to confess. Now we take a look at the relation function of agent B. What if agent A confesses? Then agent B has to compare between to confess and not to confess, minus 500 and minus 800. And it is clear that minus 500 is better. Therefore, if agent A confesses, then agent B confesses too. The second relation function of agent B. What if agent A doesn't confess? Agent B compares between minus 100 and minus 200. And here you will see that again that agent B chooses to confess between minus 100 is better than minus 200. Therefore, the second relation function of agent B. If agent A doesn't confess, agent B confesses. The dominant strategies of agent A and agent B are to confess. And here we see that the matching between the relation functions of both players is the relation function number 1 of each player, which stays in the same cell. And the result is to confess. Here is the Nash equilibrium. The Nash equilibrium takes place in the competitive game. The competitive game is the game where each player competes for the benefits of just his or her side and doesn't care about the social benefits or the summation of the benefits of all players, just for the individual benefits that they care. And here you see agent A confesses and agent B confesses, and the payoffs, both of them are heavily punished by minus 500 U-tunes. This is the Nash equilibrium in competitive game. However, you see another choice and another payoff. If both of them don't confess, they will receive just only the slight punishment, and the payoff is just minus 200 and 200. Here, it is a better payoff, compared to both of them confess. This is called the Pareto Optimality, because it is the best solution in this game. It is the win-win situation. Here, Pareto Optimality takes place in cooperative game. If they can cooperate, if they can tell each other, don't confess, before the separation to the different rooms. So, if they just has a chance to tell each other, don't confess, they will receive Pareto Optimality. You see that it is clear when there is a chance for both agents to communicate, they can turn the competitive to cooperative game, so they can change the payoff. The payoff that differentiates between the win-win situation at the Pareto Optimality and the lose-lose situation when they cannot communicate. So you see that the cooperative game yields the win-win situation, while the competitive game yields the lose-lose situation. And you can see that the Pareto Optimality yields the highest social welfare, which is calculated by the summation of all the payoffs. You can see the green box, minus 200 plus minus 200. The summation of them is just minus 400. Whereas in the red box, so the payoffs of the lowest social welfare, minus 500 plus minus 500, it is minus 1000. So the summation of the payoffs is the social welfare. And here you see that for the cooperative game, it is the maximized social welfare at the Pareto Optimality. But for the competitive game, it yields the lowest social welfare. In technical terms, the Pareto Optimality is defined as a player cannot gain more benefits unless making another player lose some benefits. In a more technical term, a player cannot be better off unless making another player worse off. You see that we have the jargon better off and worse off. Here you see that agent A can gain more from minus 200 to minus 100. But he must make agent B lose more from minus 200 to minus 800. Therefore, minus 200 and minus 200 at that point is, by technical definition, the Pareto Optimality. By this example, I will summarize the Pareto Optimality again. Pareto Optimality is the best solution that the game can use, and it is the win-win situation, and it maximizes the social benefit. And by technical definition, a player cannot gain more benefits or better off unless making another player lose some benefits or worse off. And that's what we have learned in this class. Cooperative game is the best game to achieve the Pareto Optimality. Communication is the heart of the cooperative game, and we must find a win-win situation in any set of situations between making decisions.
Today, I will show you how to solve the sequential game. It is the extension of the game theory. We have learned about the simultaneous game, and you can see that we have many types of simultaneous game, and we solve them by many different methods. For example, dominant strategy and Nash equilibrium. And if you have more than one Nash equilibrium or no Nash equilibrium at all, then you have to use the mixed strategy and the probability to find the tendency that both players will do, and then you will find the last solution, that is the focal point equilibrium, as suggested by Thomas Chirling. Today it is another game that may change about your thought, because it is not the players that move simultaneously, but one player move first and the second player move later. We call it the sequential game. So you see that one player may have an advantage over another player because they know what another player will react. I will draw the tree of the game, and then let's see what would happen. So follow me. In this sequential game, suppose A is the player who moves first. A can choose to go left and to go right. After that, we have player B to move later. Player B can decide to go left or to go right. This is like a tree. You see that A decides to go left and B can decide to go left or right. And A decides to go right and B can decide to go left or right. Here, and we have the payoffs here at the end of the tree. So you see that if A go left and B go left, what would happen? You can dance over here. If A go left and B, another player go left, so They don't crash. They don't crash. And here, both of them happy. So here 100 and 100, happy and happy. Because they don't crash to each other. But if A goes left and B goes right, then they crash and they hurt. Both of them hurt. Then minus 200 and minus 200 over here. After that, if A goes right and B goes left, here they crash and minus 200 and minus 200. And if they choose the same thing, they don't crash, and it is 100 and 100. Let's see what would happen. We have to think about A first. I have to think about the reaction function of B. Taking into account the reaction function of B. For example, if A goes left, if A goes left, then B can choose between 100 and minus 200. What would B choose? What do you think? What would B choose? We have to choose 100 over minus 200 because 100 is more than minus 200. Therefore, B will go left too. So this is A knows that B will go to the left. If A goes left and B goes left, this is the reaction function of B. And here, if A goes right and then B goes, B has to think about 100 and minus 200 again. Therefore, B will go right because 100 is more than minus 200. And here is another reaction function of B. You see that if A goes left, then A knows that B will go to the left too. And if A goes to the right, then A also knows that B will go to the right too. And now we compare the payoffs. Here, if A goes to the left, B goes to the left, and both of them get 100 and 100. And here, if A goes to the right and B goes to the right, then both of them get 100. Here's a very simple example, and you can ensure that no matter A goes to the left or to the right, they don't crash because B will choose a better way to avoid the crash. Simple, easy. And both of them will end up with happiness. 100 and 100 for every situation. But if we change the payoff, think of here 200 and 200. What would happen? If A goes to the left, B goes to the left, and both of them get 200. And here, if A goes to the right and B goes to the right, and both of them get 100, which one is better? For A will be the one who chooses the move because A moves first. Then A chooses the move. What do you think? A will choose left or A will choose right? If A chooses left, then A will get 200. And now if A chooses right, A will get just only 100. Which one is better? 200 for sure. Then the game will end up at A will go to the left because 200 is more than 100. And B will react to go to the left too. This is the solution of the game, equilibrium. And the payoffs, A will get 200 and B will get 200. Easy. This is very easy. This is how you solve the sequential game. So, let's go to next example. In the previous example, A and B are good friends. They wish the happiness for each other. Therefore, okay, I would like to catch you and I would like you to happy too. The social benefit is the payoff of A plus payoff of B. In that case, the social benefit is 200 plus 200 equals to 400. If 400 is the largest one, in all the payoffs, or the largest one among the payoffs, then it is the Pareto Optimality. This is the Pareto Optimality. Very good. You can think of another kind of game that people may not want another player to be good or to have a good result. For example, zero-sum game. You can think of another kind of game that a player has to compete with another player and the results end up with zero-sum of the payoffs. Therefore, it is the zero-sum game. Here, for example, A, we do something, so choice 1, and we have choice number 2 over here, and B can think of choice 1 and choice 2 over here, and the payoffs. If it is the zero-sum game, then probably 100 and minus 100, 200 and minus 200, 300 and minus 300, 400 and minus 400. You may ask, why B has the minus ever, always have the negative payoff? Because this is the advantage of A, who moves first. A has to choose something that can yield the positive payoff for him or for her, and let another one get the worst payoff. And all of the results are zero-sum. 100 minus 100, 0. 200 minus 200, 0. 300 and minus 300, 0. And this is also 0. Now, what would happen if A chooses choice number 1, then B will choose choice number minus 100 and minus 200. A choose 1 and B will choose 1, because minus 100 is more than minus 200. And another relation function, if A chooses 2, then B chooses minus 300 and minus 400. Which one is better? Of course, minus 300 is better. Therefore, B will choose 1. Now, think of the payoffs here. If A chooses 1 and B chooses 1, A will get 100, B will lose 100, and here if A choose 2 and B will choose 1, A will get 300 and B will get minus 300 or lose 300. So which one is better for A? Sure, 300 and 100. 300 is better. Therefore, A will choose number 2 and B will choose number 1. And here is the solution of the game. So the game will end up at the equilibrium of 2 and 1 and the payoffs of 300 and minus 300. Here is the solution of the zero-sum game. So let's see the next example. Now we consider a game, but not zero-sum, but one will gain and one will lose. Here, A again choose choice number 1 and choose choice number 2, and then B can choose choice number 1 and choice number 2 as well. Here, B1 and B2. The payoffs is very interesting over here. You can see that B will regret forever, and here B will be hurt of minus 100, here B will be hurt by minus 300, here B will be hurt by minus 100, and here B will be hurt minus 300. You see, in this kind of game, it is of course that B will choose 1 over choice number 2 because minus 100 is better than minus 300. A knows about that. But look at payoffs of A. For example, A, think of here 400. A, think of here 200. For example, no. I switch a little bit. Yes, 400 and this is 200. And here, this is 500 and this is just no, this is not okay. 200 is okay, and here just only 100. Let's look at the relation function. Here, if A chooses 1, then B will choose 1, of course, because minus 100 is better than minus 300. Here, B1, 2. And if A chooses choice number 2, B will choose choice number 1, of course. And look at the payoffs here, 400 and minus 100. And here, 500 and minus 100. Not surprised. 500 is better, 400 is better. Then A will choose 2 and B will choose 1. The game ends up the same. Here, 2 and 1. Now the payoff is 500 and minus 100. I changed a little bit in this game, and you will see the surprise. From minus 100 here, then minus 300, 250, for example, 250. The relation function is the same because B considers that minus 250 is better than minus 300, then B will choose 1, no matter. But here you see that this is 250, this is 100. What will be the equilibrium? If A is rational enough, then A will choose 500 over 400 and A will choose strategy number 2, not 1. But look, If A hates B a lot and wants B to be hurt more, what would happen? A think that B will be hurt. You lose 250 over here, but you lose just only 100 over here. And everything that I want B to lose more. I get just only 400 is okay, but I want B to lose more. A hates B. In this case, A don't want just only his or her happiness, but want another side to be hurt. Then the equilibrium in this case will change to be A will choose number 1 and B will choose number 1, and the payoffs will be 400 and minus 250. Therefore, you see something very surprising. It depends on the objective of the player, especially the player who moves first. If the objective is just focus on himself or herself, then the equilibrium will be 500 and minus 100 here, because he or she maximizes his or her utilities. But if the objective is to hurt another one hard, the hardest choice is 400 here and minus 250. Then the equilibrium will be 1 and 1 with a payoff of 400 and minus 250. So it depends on objective. The equilibrium depends on the objective. Of player who moves first. This is the first mover advantage, because the first mover can choose the objective of the game. Point. First mover's advantage. Because the first mover can choose the objective of the game. To make both happy or to hurt someone hard, to punish someone. They can choose Pareto Optimality, which is the best choice, the highest social benefit. Or they can choose to punish another player hard. So this is the first mover's advantage. Not only the objective, the first mover can choose the strategy. The strategy that leads to the objective. So you see in the sequential game, we have one side that takes advantage and another side that is disadvantage. And it is the first mover's advantage. In businesses, they're trying to be the first mover, but not all of them are successful, because some other businesses or some other firms can imitate the product, and it is the second mover's advantage. Here is another story. Then first mover innovate. Of course, if there is no imitator, copier, then the firm will occupy the whole market, monopoly power in the market. But the second mover, then the firm who moves second, imitate, copy. Then the firm can make money without spending of R&D investment and save the cost and gains a lot, and push the first mover to have less profit. So this is the second mover advantage. I would like you to draw a tree with first mover, for example, firm A, and second mover, for example, firm B. Draw a tree with firm A and firm B, and try to create the tree and ends up with the payoff that B is advantage forever, because B is the imitator and imitate everything that A create or innovate. Then you do this for homework, the challenge of this class. I will ask whether someone can do it. And of course, it is very good to be included in the examination. Let's try to create a tree for the second mover's advantage. I hope that you enjoy the class and see you in next class. Today, goodbye. 再见. สวัสดีครับ
Welcome to the last chapter of How to Do Research in Microeconomics. This is Chapter 5, Applications of Microeconomic Theory for Doing a Research. After we have discussed many things from Chapter 1 to Chapter 4, now I would like to summarize the principle of doing research in microeconomics. Principle number 1. Always use theory. We have three major theories in microeconomics. First, consumer theory. Second, theory of the firm. And third, game theory. For the first theory, the consumer theory, it emphasizes on utility, preferences of consumer, and decision-making of consumer. The target of this theory is to maximize utility. The second theory focuses on the profit of the firm and the conditions of market that makes the profit more or less. The competition between firms. And the third theory, game theory, is uncertainty between agents. It is not the decision under uncertainty, just only one person or one firm, but interactions among firms and persons. If you write your thesis just by your thought without these theories, you are at risk. At least 4 things. First, The rationale is not microeconomics. Second, the topic is not microeconomics. Third, the way that you find the answers is not microeconomics. And fourth, the results are not related to microeconomics. So keep in mind that you have to use theory always. Principle number 2, always link to reality. As we have heard about sense of industry, you have to know about reality around you and look at the problems in reality, in the real world, not just the imagination that you think, that is the problem. But find out the problems that occurs in reality. Then you find a linkage between that problem and the industry. I'm so sure that any problem can be linked to at least one industry. If you are hungry, it links to food. If you are thirsty, it links to beverage. If you are tired, it can be linked to massage. Anything can be linked to industry. However, with the sense of the industry, you have to dig deeper and deeper into that specific industry. Otherwise, you know less than the reader. And your information or your work or your thesis will not be valuable enough for the readers. In contrast, if you can produce valuable information, then it will be useful knowledge, not just for you, but for people, for public. Therefore, always link to reality. The last principle, always be scientific. When we think of microeconomics, we think of a science of microeconomic behavior, and we separate the behaviors of firms, of persons, individuals, and interactions among them. When it is scientific, then it must have 3 characteristics. First, it must be reproducible. Second, it must be provable. And third, it must be falsifiable. For the first characteristic, reproducible, if you use a set of data to conduct an experiment or to conduct a research, and you figure out a set of results, then you can map that set of data to the set of results. Another one who used the same data and the same method must find out the same thing, must reproduce your results with the same set of data and same method. This is reproducible. If it is not like this, then your method is not scientific. Second, provable. If you find out the result from a cause, from a reason, then you must find a logical way to explain why that reason explains the result. It is not like a magic that results appears without the reason, or it is not automatically linked between the result and the reasons without any logic. Therefore, you have to prove the relationship between the results and the reason. The proof can be mathematical or can be logical. So, economists use heavily mathematics. You should practice doing the proof by using mathematics, especially in microeconomic topics. And the last one, falsifiable. It means that your results can be false if some other evidences show that it is false. So, there is a room to show that your results or your conclusion can be false. If it is not falsifiable, it means that nothing can show that your results can be false. Why? Because you shut all the doors that can prove that you are false. If it is like this, it means that you are always correct. And if something is always correct and cannot prove that it can be false, this is not scientific. Science must be tested. Science must be changed over time from new evidences. Science must be ensured that it is still true. Science can be false. So, these are signs. Falsifiable. Microeconomics would like to show the power of being a scientific discipline. Therefore, it is subjected to this principle, being scientific. In your research, you have to bear in mind these three principles. Always use theory, always linked to a reality, and always be scientific. Then your work will be at a high standard, an international standard. It can be accepted by all scientists in microeconomic disciplines. And your thesis can be published in a good international journal. And this is always good for you, for your graduation. I come to the end of the lecture of Economics 708. I would like to thank Dr. Supanika again for letting me to have a chance to come to talk to you about how to do research in microeconomics. I thank you a lot for your attention in participating in this class until now, and I wish you to have success in doing microeconomic research. If you have time to do a small project or a small research in microeconomics, try to follow my suggestions, and then I hope that we have an opportunity to talk together more and discuss more about many things that you would. Thank you very much again, and have a nice day. See you again. 再见 Goodbye สวัสดีครับ